Hey guys, it's good to be back and be able to do some lessons with you. So the last lesson I did with you, I wasn't able to appear in person, but it was on binding energy. And you guys did beautifully with it. I was very proud of you. And what we found with binding energy is that when you start with protons and neutrons and put them together to make a nucleus, that somehow when they form the nucleus, some of the mass that was originally present disappears from the universe. So the mass of 2 protons and 2 neutrons is greater than the mass of the helium nucleus that is formed by them. And this mass that disappears from the universe turns into energy. The energy leaves the nucleus, and in order to break the nucleus back apart, you'd have to put that energy back in. So the bigger the binding energy, the more stable your nucleus is going to be. I had you guys practice a random element. You worked through it beautifully. You got your binding energy in mega electron volts. And then the last step is you divide by the number of nucleons, particles in the nucleus, and that's the number that's most important. And when you plot out the number of nucleons in different isotopes, you get a graph that looks like this. And although it might not look like much, this graph is actually very important. You'll see there are a few elements whose binding energy is way higher than their neighbors. That's key. If an isotope has a greater binding energy than its neighbors, it will be a very stable isotope. If, on the other hand, your binding energy is much less than your neighbors, it's likely that you are going to decay and turn into one of those more stable isotopes. You'll also notice how the binding energy drops off as we get bigger and bigger nuclei, and that's why bigger nuclei tend to be very unstable. When you plot out every stable isotope known to humanity, you get what's called the band of stability. And you'll notice that for small elements on the periodic table, the way you make a stable isotope is with almost equal numbers of protons and neutrons. So if you look at something like oxygen, it'll have an atomic number of 8 and a mass number of 16, which means it's perfectly balanced between protons and neutrons. And that's a trend for almost every small isotope. Once you get past around potassium, calcium, you're going to start to see that they're no longer going to be equal. Once you hit that point, there's going to be a lot more neutrons required to counterbalance the repulsion between the positive protons. Okay, so I just want you to know the trend. Small isotopes tend to be stable with equal numbers of protons and neutrons, and the bigger ones require a greater number of neutrons to hold it together. At one point in human history, people thought atoms were formed in the first creation, and the nucleus could never change. Sure, they could react with other elements and form compounds and molecules, but you couldn't change oxygen into something else. Once oxygen, always oxygen. Okay, and this was an idea that Newton himself championed, that nuclei, that elements were unchangeable. It turns out that that held sway for quite a while, but it turns out in the early 1900s, late 1800s, some evidence started to appear that cast doubt on that idea. And the person I'd like to highlight is this scientist who I'm sure you've heard of before. Probably not with her maiden name, her original name, but her married name, Marie Curie. She is the first one who we are going to credit with discovering the fact that one element could turn into another. And she got the Nobel Prize for this, once in physics and once in chemistry, for all the contributions that she made to both fields. And the element that we'd like to look at is the element polonium-210. Polonium is actually an element discovered by Madame Curie, and she named it after her native Poland. So polonium-210. And what she found is that the polonium-210 would have particles shoot off of it. And these particles would cause the polonium to change into other elements, a different isotope. We call these alpha particles because we didn't know what they were at the time. They were the first radioactive particle discovered, and therefore they named it alpha after the first letter of the Greek alphabet. It now turns out that these alpha particles are actually helium nuclei. No electrons around them, but 2 protons and 2 neutrons. A very stable configuration for a very small nucleus. Okay, so she saw these shoot out, and she saw the polonium turn into some other element. We'll learn how to predict that in a little bit. And when we look at our isotope sheet that you guys have, you'll see that we have beta decay, and we have some that are alpha decay, and some that are gamma decay. Beta decay refers to the second particle, radioactive particle that people found coming off of a nucleus. This was found by this gentleman, Henry Becquerel. He was from France, and he found that some elements, some isotopes, would have a very tiny particle shoot out. It wasn't an alpha particle. It turned out that it was an electron. And what was weird about this electron is it did not come out of the shells where electrons are supposed to be found, but somehow it was popping out of the nucleus itself. How in the world did the electron get there? And what made it shoot out? Well, it turns out we now know that it wasn't there all the time. We know that neutrons have a certain arrangement of quarks, and protons have a different arrangement of quarks. And it turns out that if you can get one of these down quarks to flip, that is to turn from a down quark to an up quark, all of a sudden your item will go from 0 charge. Again, these quarks have charge to them, but they're all balanced in a neutron, to one where we have a charge of +1. And when that flipping takes place of one of these quarks from a down to an up, off will shoot a small negative charge that we call an electron. Back then they called it a beta particle. And this beta negative particle shooting off conserves charge. So we start with no net charge, and afterwards we have no net charge. Very important idea. Charge is conserved in all reactions. You can't just have a positive charge appear without a negative charge balancing it out. So what was happening with these is neutrons were turning into protons inside the nucleus. We now know that that would happen when we had isotopes that had too many neutrons in them. They would give up their neutron, turn it into a proton, and become a more stable isotope. So it's driving these decays, whether it was alpha decay or beta decay, with the desire to become a stable isotope. Stable meaning it has more binding energy per nucleon than its neighbors. It turns out we had another type of decay, and it turns out it was the same particle that we were getting with beta decay, but it was positively charged. That's bizarre, because that means it's a positively charged electron. And these positively charged electrons were shooting out of the nucleus of some elements. Some isotopes were giving off positive electrons. These are called positrons. And as crazy as it is, these positive electrons don't belong in our universe. They are what are known as antimatter. And if these positive electrons meet up with a normal negative electron, both particles will disappear from the universe and energy will take their place. Again, what's actually happening to make this positive electron appear out of nowhere is we are having an up quark flip to a down quark. So again, we had a proton that was up, up, down, and one of the ups turns into a down, and we go from a +1 charge to neutral. How did that happen? It's because the positive electron carried away the charge. We still have a charge of +1, it's just no longer located in the nucleus. Okay, so this is called beta positive decay, and it's when a proton turns into a neutron. Why would this happen? That would be for isotopes that have too many protons. It would be in this section of our band of stability. A proton would turn into a neutron, and the isotope would move closer to and maybe onto the band of stability. The final type of decay is called gamma decay. It turns out that gamma is not a particle at all. It turns out that gamma is just a type of light. High energy, high frequency light. The gamma comes off when you have a nucleus that has excess energy. It gives off a little bit of energy without changing the element, and it becomes a little more stable, a little more controllable. Okay? This one is not as important because nothing actually changes in the nucleus other than the amount of energy. Okay? It's like giving the nucleus a little bit more binding energy by having a little bit of mass turn into gamma and leaving the nucleus. Okay, and that's where we're going to end for today. I don't want to give too much in one day. I know this is a lot to absorb, and we'll actually be learning how to make predictions from all of this starting tomorrow.